We're about to talk about an element that's, well, it's pretty much everywhere, in everything. It is quite literally the foundation of the world as we know it.
So, what makes one single element the king of the periodic table? I mean, really, what gives it the power to be the foundation for, well, so much of everything?
Think about this. This one element, it can arrange itself into the hardest natural substance we've ever found.
But then, and this is where it gets crazy, that exact same element can also form one of the softest, most useful materials out there, something you probably use every single day. And if that whole hardest, softest thing wasn't enough to blow your mind, get this. It is the undisputed, fundamental building block of all known life.
The element we're talking about, of course, is carbon, the versatile superstar behind diamonds, the lead in your pencil, and, well, you.
You know, what's absolutely fascinating is that carbon is actually kind of rare here on Earth. I mean, it's a tiny, tiny fraction of our planet's crust and atmosphere. But get this, it's the fourth most common element in the entire universe. And it's the absolute backbone of every single living thing. So what's its secret? How does it pull that off?
Okay, so to really get a grip on carbon's power, we have to start with its biggest problem. A real chemical identity crisis, you could say. It all comes down to its atomic structure. Carbon's atomic number is 6. So you've got 2 electrons in that inner shell, and then, this is the important part, 4 electrons in its outer shell, the valence shell.
And here's the dilemma. See, like all elements, what carbon really wants is to be stable. It wants a full outer shell with 8 electrons. But it's only got 4, so it's stuck, right in the middle. It's halfway there, which is kind of the worst place to be. It's got 2 choices, and honestly, they're both terrible. Option 1, try to grab 4 more electrons. The problem, its little nucleus just can't handle all that negative charge, and the whole thing becomes unstable. Okay, so option 2, what if it just gets rid of the 4 it has? Well, that takes a huge amount of energy, way more than it has to spare. So it's completely stuck. It can't win.
So what's an atom to do? Well, it finds a third way, a much more elegant, clever solution. And this solution, this is the source of all its power.
When you can't gain and you can't lose, what's left? You share. And that one decision is carbon's secret. It decides to share.
This act of sharing creates something called a covalent bond. It's brilliant, really. Instead of fighting over electrons, carbon basically forms a partnership. It says, hey, you put one in, I'll put one in, and together they create that stable, shared outer shell they both want. It's the ultimate chemical workaround.
And this superpower of sharing, it unlocks 2 more incredible abilities. Get ready for these terms: tetravalency and catenation.
Let's start with tetravalency. It's a fancy word, but the idea is simple. Because carbon has those 4 outer electrons to share, it can form 4 strong bonds all at the same time. I love this analogy. Think of it like having 4 hands instead of just 1 or 2. This lets it connect in all sorts of directions and build these amazing, complex, 3-dimensional structures.
Okay, superpower number 2, catenation. This one is really special. It's carbon's unique ability to bond with itself. It can link up to form these super long, super stable chains and rings. This self-linking thing is incredibly rare in the periodic table, and it is the key to creating the massive, complicated molecules that life itself depends on. All right, so we've got sharing, we've got 4-way bonding, and we've got self-linking. With a toolkit like that, what can carbon actually build? Let's take a look.
The answer is it can build something called allotropes. Basically, these are just different physical forms of the exact same element. We're talking identical chemical makeup, but they look and act completely different, and it all just depends on how those carbon atoms are arranged.
The most famous ones you've definitely heard of. Diamond, for one. Graphite, like in your pencil. And then there are the more recently discovered fullerenes, which are these amazing molecules that can form hollow shapes, kind of like tiny soccer balls.
And the difference between diamond and graphite is the perfect example of this. In a diamond, every single carbon atom uses all 4 of its hands to grab onto 4 other carbons. This creates this super rigid, tight 3D lattice, which is why diamonds are so incredibly hard. But now look at graphite. Here, each carbon atom only bonds to 3 others. They form these flat sheets that can slide over each other. And that one leftover electron, it's free to roam around, which is what makes graphite soft, slippery, and able to conduct electricity. It's the same element, but they are worlds apart, just because of how they're holding hands.
Okay, let's bring this all back home.
Why do we care so much about one element's bonding strategy? Why does this matter to us? It really all boils down to this. Catenation, that self-linking power, lets carbon build long, complex backbones for molecules. Then, tetravalency, its 4 hands, lets it attach all sorts of other elements in every direction. That combination right there, that's the recipe. That's what allows it to create the huge, stable, and incredibly diverse molecules, everything from our DNA to the proteins in our cells that make life possible.
So, you see, carbon is the element of our past and our present. Its unique chemical toolkit has literally built the world around us and the very bodies we live in. The only question left is, with these new forms, like fullerenes, opening up entire new fields like nanotechnology, what future will we build with it next?